Hello, settle in and make yourselves comfortable. Close your eyes and picture the night sky. Countless pinpricks of light scattered across that velvet blackness. Have you ever stared into that abyss and wondered, where does it all end? Does this seemingly boundless cosmos have a wall, a boundary, a final frontier? For a long time, this was a question reserved for philosophers and poets. But today, physicists and astronomers are attempting to answer it. And frankly, their answer is far more astonishing and complex than we could possibly imagine. They don't just assume the universe has a boundary, they've found it. And here's the most astounding part. This edge is not static. It's moving. Today, we are embarking on the longest journey imaginable, a trip to the very edge of the observable universe. We will explore what this edge is, how it was discovered, and why its movement holds the key to understanding the ultimate fate of everything. Get ready. We are diving into the cosmos' greatest mystery. To truly understand what the edge of the universe means, we first need to clarify our terms. When we say the universe, what exactly are we talking about? Modern cosmology divides this concept into two distinct ideas. First, there is the capital U universe, the theoretical totality of everything that exists. Its true size is unknown to us. It may even be infinite. Then there is the observable universe. This is the portion of the cosmos from which light has had time to reach us since the beginning of time. The key factor here is age. The universe is approximately 13.8 billion years old. Since light travels at a finite speed, we can only see objects whose light has been traveling toward us for less time than that. Imagine you are standing on a ship in the middle of the ocean. You see the water stretching to the horizon, but you know the ocean doesn't actually end there, right? Your view is simply limited by the curvature of the Earth. The observable universe is a similar story. Its boundary isn't a brick wall, it's what we call the cosmological horizon. This is the farthest point in space-time that we can currently observe from Earth. This is the boundary we are focusing on today, the horizon beyond which lies either much more of the universe or something currently unfathomable. So let's start our deep dive with the most fundamental question. Where did the idea that the universe might have an edge, or at least a beginning, even come from? For most of human history, the dominant concept was a static, eternal, and infinite universe. Even the great Albert Einstein, when developing his general theory of relativity in 1915, initially assumed the universe was unchanging. His equations, however, told a different story. They predicted that the universe couldn't be static. It had to be either expanding or contracting under the influence of its own gravity. To fix this discrepancy with his existing worldview, Einstein introduced the so-called cosmological constant into his equations, a hypothetical force that countered gravity and kept the universe in perfect equilibrium. He would later call this his biggest blunder. The breakthrough finally came in the 1920s. First, the Russian mathematician Alexander Friedmann, solving Einstein's equations without any ad hoc fixes, showed that non-stationary time-varying solutions were completely natural. Then in 1929, the American astronomer Edwin Hubble made his epoch-making discovery. Using the most powerful telescope of the time at the Mount Wilson Observatory, he observed distant galaxies and noticed a stunning pattern. Almost all galaxies were moving away from us. Furthermore, the farther a galaxy was, the faster it seemed to be speeding away. This phenomenon, known as Hubble's law, became the first observational proof that the universe is expanding. It was a revolutionary insight. If the universe is expanding today, it must have been smaller in the past. And if we rewind time far enough, all matter, all energy, all space and time itself must have been compressed into a single, infinitely dense and hot point. This state was named the singularity, and the moment of its explosive expansion was termed the Big Bang. This model gave us the concept of the universe's age and, consequently, the idea that our observable portion must be finite. The edge of the universe is a direct consequence of its birth at a specific point in time. It isn't a boundary in space, it is a boundary in time that we observe today. Now let's explore this boundary in more detail. What exactly do we see when we look out to the farthest reaches of our cosmological horizon? We don't see darkness, and we certainly don't see a solid wall. We see light. This is incredibly ancient light, often referred to as the first light of the universe. This phenomenon is formally known as the cosmic microwave background, or CMB radiation. To truly understand its nature, we need to travel back in time to an epoch when the universe was only about 380,000 years old. By modern standards, that's just infancy. Back then, the universe bore no resemblance to what we see today. It wasn't the cold, empty cosmos. Instead, it was a searing, hot, dense fog, a plasma, made up of protons, electrons, and photons, which are particles of light. The temperature of this primordial soup was so high that electrons couldn't settle down with protons to form stable hydrogen atoms. They remained free, constantly colliding with and scattering the photons. For light, the young universe was completely opaque, much like a dense fog or the surface of the sun. Photons simply couldn't travel any significant distance without hitting a charged particle, but the universe continued to expand and, consequently, cool. And so when its age reached that pivotal 380,000-year mark, the temperature dropped to about 3,000 Kelvin. At this temperature, the particles no longer had enough energy to resist the electromagnetic attraction. Electrons began to be captured by protons, forming the first neutral hydrogen atoms. This pivotal process is known as recombination, and at that exact moment, everything changed for light. The space, now cleared of free electrons, became transparent to photons. The light that had previously been trapped within the plasma fog was finally released, racing outward in every direction. It is this very light, emitted simultaneously from every point in the then tiny universe, that we observe today as the cosmic microwave background. It has traveled through the cosmos for 13.8 billion years, and during that time, the expansion of the universe has dramatically stretched its waves. Initially, this was bright, orange-red light, but today it arrives as microwaves, completely invisible to the human eye. This surface of last scattering, as astrophysicists call it, is that boundary, the true edge of the observable universe. We are literally seeing the glow of the infant universe at the very moment it became transparent. The story of how the cosmic microwave background was discovered is itself a perfect example of how major scientific breakthroughs often happen purely by accident. The existence of this echo of the Big Bang had actually been predicted theoretically back in the 1940s by physicist George Gamow and his colleagues, Ralph Alpher and Robert Herman. They were working on the hot Big Bang theory and calculated that residual heat from the universe's original fireball should still permeate all of space, but only as radiation just a few degrees above absolute zero. However, technology at the time made testing this hypothesis impossible, and the prediction was gradually forgotten. Nearly 2 decades passed. In the mid-1960s, 2 American radio astronomers, Arno Penzias and Robert Wilson, were tuning a large horn antenna at Bell Labs in New Jersey. It had initially been built for early satellite communication experiments, but they had since repurposed it for radio astronomy observations. Right from the start, they faced an inexplicable problem. The antenna picked up a faint but constant background noise that seemed to come from every direction. It didn't change day or night, or with the seasons. The signal was perfectly uniform no matter where they pointed the antenna. The scientists assumed the problem lay with the equipment. They checked every system and resoldered the connections, but the noise wouldn't go away. At one point, they even suspected the culprits were a pair of pigeons that had nested inside the horn, leaving behind what one scientist famously described as white dielectric material. They evicted the pigeons and meticulously cleaned the antenna, but the mysterious noise persisted. In despair, they were ready to accept this static as an unavoidable interference. But, by a stroke of luck, Penzias learned that a group of physicists at Princeton University, led by Robert Dicke, were actively building a detector specifically to search for the very background radiation Gamow had predicted. Penzias contacted Dicke, and suddenly everything clicked into place. The noise Penzias and Wilson thought was just static was the ancient light of the universe the theoreticians were looking for. They had accidentally stumbled upon the greatest confirmation of the Big Bang theory. For this groundbreaking discovery, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics in 1978. Their accidental finding transformed cosmology from a field of theoretical speculation into a precise observational science. While Penzias and Wilson's discovery was monumental, it only provided the first, most generalized glimpse of the cosmic microwave background. Their observations revealed that this radiation was startlingly uniform. No matter where they looked, the temperature remained the same, around 2.7 Kelvin. This isotropy, this uniformity in every direction, was in itself powerful confirmation of the cosmological principle, which posits that on large scales, the universe is homogeneous and isotropic. However, theory dictated that this uniformity couldn't be perfect. If the early universe had been absolutely smooth, lacking even the slightest density fluctuations, gravity would never have been able to form the structures we see today: galaxies, clusters of galaxies, and the colossal cosmic voids. There had to be tiny, microscopic irregularities, or seeds, within the density of the primordial plasma, acting as the starting points for future galaxies. These slightly denser regions should have left their mark on the CMB map in the form of subtle temperature variations known as anisotropies. Detecting these fluctuations was an immense challenge. They were predicted to be incredibly small, on the order of just 1 part in 100,000 of a degree. Ground-based telescopes couldn't handle this task due to interference from Earth's atmosphere, meaning a space-based instrument was necessary. That instrument was the NASA satellite named COBE, the Cosmic Background Explorer, which was launched in 1989. It scanned the sky for 2 years, and in 1992, the project team announced the long-awaited discovery. COBE created the first-ever map of the CMB temperature fluctuations. This map, which resembled a fuzzy photograph, revealed slightly hotter red spots and cooler blue spots. It was, without exaggeration, a photograph of the universe in its infancy. George Smoot, one of the project leaders, famously commented on the discovery, stating, "If you're religious, it's like seeing the face of God." These spots were exactly the primary irregularities cosmologists had been searching for. They confirmed that the universe possessed structure from the very beginning, and it was from these tiny ripples in space-time that the entire majestic structure of the cosmos grew over billions of years. The COBE discovery marked the second great breakthrough in the study of the early universe and earned its leaders the Nobel Prize in 2006. The map produced by the COBE satellite was revolutionary, but its resolution was quite low. While it confirmed the existence of these fluctuations, it didn't allow scientists to study them in detail, and those details were critically important. By analyzing the size, distribution, and amplitude of these hot and cold spots on the cosmic microwave background map, cosmologists could act like detectives, piecing together the key parameters of our universe, its exact age, geometry, and the density of ordinary matter, dark matter, and mysterious dark energy. It's comparable to determining a drum's size, shape, and material simply by studying the pattern of its vibration. This necessity drove the development of more sophisticated instruments. In 2001, NASA launched a new space probe, the Wilkinson Microwave Anisotropy Probe, or WMAP. Its mission was to compile a significantly more detailed map of the relic radiation. WMAP scanned the skies for 9 years, and the results exceeded all expectations. The map it delivered was tens of times sharper than COBE's, allowing us to discern the fine structure of those primordial fluctuations. Analyzing this data allowed scientists to determine the fundamental properties of our world with unprecedented accuracy. It is thanks to WMAP that we now know the universe is 13.77 billion years old, with an error margin of less than 1%. We learned that the universe has a flat Euclidean geometry, meaning parallel lines will never cross. Crucially, WMAP gave us the universe's precise recipe. It revealed that ordinary matter, the stuff that makes up stars, planets, and us, accounts for only 4.6% of the universe's total mass energy. Another 24% is mysterious dark matter, an invisible substance detectable only through its gravitational effects. The remaining 4% is something even stranger, the dominant component of the universe, now known as dark energy. But the search for precision didn't stop there. In 2009, the European Space Agency launched the Planck Observatory. Utilizing even more sensitive detectors, cooled almost to absolute zero, Planck created the most detailed map of the cosmic microwave background to date. Planck refined WMAP's data and allowed scientists to test the subtlest predictions of the standard cosmological model. These three missions, COBE, WMAP and Planck, transformed the study of the universe's edge from qualitative observation into quantitative science. We aren't just seeing this edge, we can read it, extracting fundamental information about the structure and history of our world. Now that we've established the edge of the universe is actually the light from its infancy, let's address the second part of our headline: it's moving. What exactly does that mean? In the everyday sense, when we say something is moving, we mean an object is shifting from one point in space to another. But with the boundary of the universe, things are much more complex. It's not moving through space, space itself is moving. As we've discussed, Edwin Hubble discovered that the universe is expanding. Galaxies aren't scattering away from each other because they are flying through the cosmos like shrapnel from a grenade. Instead, they are essentially stationary within their localized space, but the space between them is stretching out. The classic analogy for this is an inflating balloon with dots drawn on its surface. As you blow up the balloon, its rubber surface stretches, and all the dots move away from one another. Crucially, the dots that were farther apart initially move away faster. In this analogy, the dots represent galaxies, and the surface of the balloon is a two-dimensional model of our three-dimensional space. It's vital to understand that this expansion has no center. To an observer on any dot on the balloon's surface, it will appear that all the other dots are moving away from them. It's the same in our universe. An observer in any galaxy will see all other galaxies receding from them. We are not at the center of the universe because the expansion simply has no center. The movement of the edge of the observable universe is a direct consequence of this expansion. The surface of last scattering, the origin of the cosmic background radiation we detect, was much closer to us 13.8 billion years ago. But in the time it took for that light to travel to Earth, space itself has stretched monumentally. As a result, the regions that emitted the light we see today are now located approximately 46.5 billion light-years away from us. This distance defines the radius of the observable universe, and this boundary is constantly moving away from us. Furthermore, it is receding at a speed that exceeds the speed of light. This is where confusion often sets in. Doesn't the theory of general relativity forbid motion faster than light? It does, but that prohibition applies only to objects moving through space-time. Space-time itself, however, can expand at any speed. Therefore, the edge of the universe isn't flying away from us, it's receding, because with every passing moment, more and more new space is being born between us and that boundary. While Hubble's observations confirmed the idea of an expanding universe, a critical question remained unanswered for decades. What would be the ultimate fate of this expansion? There were three main scenarios, all dependent on the total density of matter and energy within the cosmos. Think about throwing a rock straight up. If you throw it slowly, it will peak and then fall back down, pulled by Earth's gravity. But if you throw it fast enough at escape velocity, it will overcome the Earth's pull and fly out into space forever. There is also a critical intermediate case where the speed is just right, allowing the rock to escape, but its velocity constantly drops, asymptotically approaching zero. Cosmologists believed the universe operated on a similar principle. The collective gravity of all matter acts as a cosmic brake, slowing down the initial expansionary impulse delivered by the Big Bang. The first scenario, mirroring the rock that falls back, was called the Big Crunch. If the average density of the universe were high enough, gravity would eventually halt the expansion and pull everything back. Galaxies would begin rushing toward each other, temperatures would skyrocket, and the entire cosmos would collapse back into a singularity. This outcome describes a closed universe with spherical geometry. The second scenario, like the rock escaping forever, assumed the universe's density was too low for gravity to overcome the momentum. In this case, the universe expands eternally. This defines an open universe with a hyperbolic, saddle-shaped geometry. The third critical boundary case is the flat universe, where the density is exactly equal to the critical value. In this universe, expansion would continue forever, yet its speed would constantly slow, asymptotically approaching zero. Throughout the 20th century, cosmologists fiercely debated which of these cosmic destinies awaited us. Mounting evidence suggested we lived in either a truly flat or very nearly flat universe. Everyone expected to find definitive proof that the expansion was slowing down. Then, in 1998, two independent teams of astronomers studying distant supernovae made a stunning discovery, a conclusion that flipped modern cosmology completely on its head. The discovery made in 1998 was a genuine scientific bombshell, its significance comparable to Hubble's findings or the detection of the cosmic microwave background. Two teams of astrophysicists, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were focused on the same goal, measuring the rate at which the universe expanded throughout its history. To do this, they needed so-called standard candles, astronomical objects whose true luminosity is known. By knowing an object's intrinsic brightness and measuring its apparent brightness, scientists can precisely determine its distance. As these standard candles, the researchers used type Ia supernovae. These are specific stellar explosions that occur when a white dwarf star in a binary system siphons material from its giant companion. Once it reaches a critical mass, the Chandrasekhar limit, it detonates. Because the mass at the moment of detonation is always the same, the brightness of the resulting explosion is also virtually identical. This makes them perfect for measuring cosmic distances. By observing these supernovae in extremely distant galaxies, the scientists could look back into the universe's past and determine how fast it was expanding billions of years ago. Working independently, both groups expected to find the same thing, that the universe had expanded faster in the past than it is now. After all, gravity should have been slowing the process down, but the results were the exact opposite. The distant supernovae appeared fainter than they should have been. This meant they were further away than the decelerating expansion model had predicted. The only possible explanation was that while the light traveled across space to reach us, the universe had expanded more rapidly than anticipated. In other words, the universe isn't slowing down its expansion, it's speeding up. This conclusion was utterly shocking and contradicted all expectations. For a long time, the scientists checked and rechecked their data, searching for possible errors. But there were no errors. The results were undeniable. Some mysterious, unknown force pervading all of space was acting like an anti-gravity force, causing space-time to stretch faster and faster. This hypothetical substance was dubbed dark energy. For this revolutionary discovery, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011. The movement of the edge of the universe wasn't just motion, it was an accelerated flight. And that changes everything. So the universe contains dark energy. But what exactly is it? The short and honest answer is nobody knows. It is without a doubt the biggest mystery in modern fundamental physics. We can observe its effects, the accelerated expansion of the universe, but its true nature remains completely unknown. However, physicists do have a few hypotheses. The simplest and most popular theory connects dark energy to the cosmological constant, the very constant that Einstein introduced into his equations and later called his biggest blunder. Perhaps it wasn't a mistake at all, but a stroke of genius. In this scenario, dark energy is an inherent property of the vacuum itself, of empty space. According to quantum field theory, the vacuum is not absolute nothingness. It is teeming with virtual particles constantly popping into and out of existence. These quantum fluctuations must possess energy. And this vacuum energy, according to general relativity, should create a gravitational repulsion that stretches space. That sounds logical, but there is one huge problem. When theorists try to calculate the theoretical density of this vacuum energy, they get a number that is 120 orders of magnitude, that is, a 1 followed by 120 zeros, larger than the observed dark energy density. This is the largest discrepancy between theory and experiment in the entire history of physics. It's known as the cosmological constant problem. Clearly, our current theories are fundamentally missing something. Another hypothesis suggests that dark energy is not a constant but rather a new dynamic field permeating the universe, similar to the Higgs field. This hypothetical field is called quintessence. Unlike the cosmological constant, the density of quintessence could vary across time and space. This opens up more possibilities for explaining observational data, but it also makes the theory more complex and speculative. There are even more radical ideas. For example, some suggest that no new substance or field exists at all. Instead, the accelerated expansion is a sign that Einstein's theory of gravity itself is incorrect at cosmological scales and requires modification. Perhaps gravity behaves differently than we assume over very large distances, manifesting itself as a repulsive force. Which of these ideas is correct, or if the truth lies in a completely different plane, will be revealed by future observations. But the existence of dark energy itself is undeniable. It makes up nearly 70% of all the energy in the universe and determines its ultimate fate. The accelerated expansion of the universe, driven by dark energy, has completely rewritten our understanding of the cosmos's ultimate fate. Where we once considered simple scenarios like the Big Crunch or eternal, gradual deceleration, we now face new, far more exotic and terrifying possibilities. One of the most dramatic of these scenarios is dubbed the Big Rip. This fate is only possible if dark energy isn't merely a cosmological constant, but rather a theoretical phantom energy, whose density doesn't remain steady but actually increases over time. If this is the case, its repulsive force would grow exponentially stronger. Initially, this force would overcome the gravitational pull between clusters of galaxies, causing them to fly apart. Next, it would become powerful enough to tear apart individual galaxies, stripping stars from their orbits. But the destruction doesn't stop there. Dark energy's power would overcome gravity within stellar systems, ripping planets from their orbits and flinging them into the void. In the final stage, mere minutes before the end, this force would become so overwhelming that it would conquer the electromagnetic forces holding atoms and molecules together. Stars and planets would simply explode. And finally, in the ultimate instant, it would tear apart atomic nuclei and even elementary particles. All matter in the universe would be fragmented into components infinitely distant from one another. Space-time itself would collapse into a singularity, not of density, but of extreme rarefaction. Fortunately, current observational data makes this scenario highly unlikely. The density of dark energy appears to be constant after all. This means we are likely destined for a different, equally bleak, but far slower ultimate fate, known as the heat death or the Big Freeze. In this scenario, the universe will simply continue its accelerated expansion forever. Galaxies not gravitationally bound to our local group will recede faster and faster. Eventually, they will cross our cosmological horizon and disappear from sight permanently. Our night sky will become practically empty. Only the galaxies within our local group will remain, eventually merging into one colossal elliptical supergalaxy. Milkomeda. Over the course of trillions upon trillions of years, the last stars in Milkomeda will burn out. Star formation will cease entirely as the gas reserves are depleted. The cosmos will plunge into near total darkness, illuminated only by the faint light of white dwarfs and neutron stars. In the unimaginably distant future, even these remnants will cool, turning into inert black dwarfs. The galaxy will become a graveyard of dead stellar remnants, rogue planets, and black holes. Then, across stretches of time so vast they defy comprehension, even the black holes will evaporate through Hawking radiation. The universe will ultimately degrade into a cold, dark and empty soup of elementary particles, photons and neutrinos, a place where nothing will ever happen again. This is the final, eternal death. Let's return to the edge of our universe, the cosmological horizon. The accelerated expansion has a profound and, frankly, paradoxical effect on this boundary. We've established that the radius of the observable universe is about 46.5 billion light-years. This marks the distance to the regions that emitted the cosmic background radiation we see today. But what happens to the horizon itself? Because of the accelerated expansion, extremely distant galaxies are actually moving away from us faster than the speed of light. This means any light they emit right now will never reach us. The space between us and them is expanding faster than the light can cross it. Essentially, these galaxies drop out of our causal connection forever. We can never receive any new information from them again. They cross what we call the event horizon. This is the very mechanism that will eventually lead to our distant future sky becoming completely empty. Galaxies will disappear one by one behind this boundary. But here's the interesting nuance: we will still see their past. The light they emitted billions of years ago is still traveling toward us, so we'll watch as these galaxies become increasingly redshifted, their time appearing to slow down until they fade into ultimate darkness. It's much like watching an object fall into a black hole. To a distant observer, the object appears to freeze eternally on the event horizon, becoming dimmer and redder until it vanishes. Thus, we deal with two types of horizons. First, the particle horizon, which defines our observable universe, currently sitting at 46.5 billion light-years. This boundary will continue to expand over time as light from ever more distant regions finally reaches us. However, due to acceleration, that growth rate is slowing down and will approach a fixed limit. The second is the event horizon, presently located at roughly 16 billion light-years. Any object that is further away than this distance today, we will never observe as it is in its future state. For us, it is permanently lost. This concept paints a rather lonely picture of the future. Our universe is becoming increasingly isolated. We are living in a unique era where we can still observe billions of other galaxies. Hundreds of billions of years from now, future astronomers, if they exist, will see only our own gigantic galaxy surrounded by utter, endless void. They might not even conceive that other galaxies once existed or that the Big Bang ever happened. For them, the entire field of cosmology will be hidden behind an impenetrable horizon. But now let's turn our attention to the boldest question we can ask. What actually lies beyond the boundary of the observable universe? If our cosmic horizon isn't a physical wall, but simply a limit imposed by the speed of light, then the logical conclusion is that the universe simply continues indefinitely beyond that limit. The cosmological principle, which posits that the universe is homogeneous and isotropic on the largest scales, strongly suggests that things beyond our horizon are exactly the same as they are here, the same galaxies, the same stars, governed by the same laws of physics. We simply haven't received the light from those regions yet. How large is this hidden, greater universe? We genuinely don't know. It could be hundreds, thousands, or even billions of times larger than the fraction we can observe. Or perhaps it is truly infinite. The very concept of an infinite universe gives rise to some truly stunning philosophical consequences. One of the most mind-bending is known as the paradox of repeating worlds. If the universe is infinite, yet composed of a finite number of particle types that can arrange themselves only into a finite number of possible states, then the laws of statistics dictate that every arrangement of matter must repeat itself an infinite number of times. This implies that somewhere out there, in the unimaginable distance beyond our cosmic horizon, an exact copy of planet Earth exists, and living on it is an exact double of you, currently doing the precise same thing you are doing right now, and you have an infinite number of these identical copies. Furthermore, there are also worlds that differ from ours only by the most minor details. A universe, for instance, where you chose to wear a different colored shirt this morning, or a world where you made a pivotal life decision differently. In an infinite universe, anything that has a non-zero probability of occurring must occur. Not just once, but an infinite number of times. Of course, this is merely a logical consequence, stemming from the unprovable assumption of infinity. But the sheer philosophical scope of the idea is absolutely breathtaking. This very concept forms the basis of many modern multiverse hypotheses. Perhaps our universe is simply one among countless bubbles perpetually being generated within an ever-expanding space. This model is formally known as the theory of eternal inflation. The theory of eternal inflation stands out as one of the most popular, yet simultaneously most speculative ideas in modern cosmology. It's an expansion of the theory of cosmological inflation, which was first proposed in the early 1980s to solve several fundamental problems inherent in the standard Big Bang model. These include the horizon problem: why do separate regions of the cosmic microwave background, which never had time to interact, share the exact same temperature? And the flatness problem: why is the geometry of our universe so remarkably close to being Euclidean, or flat? The inflationary model suggests that during the very first fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion. In an infinitesimally brief moment, it inflated from subatomic scales to sizes far exceeding the portion we observe today. This super-rapid expansion effectively smoothed out all initial irregularities and space-time curvature, thereby accounting for the flatness and remarkable uniformity of our observable world. The theory of eternal inflation, put forth by physicists like Andrei Linde and Alexander Vilenkin, takes this idea a critical step further. It posits that once this inflationary process begins, it never fully stops. It ceases only in isolated regions, just as it did in our own universe, giving rise to bubbles filled with conventional matter and energy. But in the vast space between these bubbles, inflation continues forever, constantly spawning new bubble universes. In this worldview, our Big Bang isn't a singular event of cosmic creation, but merely a local termination of inflation within our corner of a much larger structure, the multiverse or meta-universe. Each of these bubbles could potentially have its own unique laws of physics, fundamental constants, and even a different number of dimensions. In some, gravity might be stronger, in others weaker. Some might permit the existence of stable atoms and stars. Others may not. Our universe is thus revealed as just one out of an infinite number, possessing parameters that, by cosmic chance, happen to be perfectly suitable for the formation of complex structures and, ultimately, life. This idea offers a possible solution to the so-called fine-tuning problem: the fact that fundamental constants, like the speed of light, the electron charge, and the gravitational constant, have values precisely necessary for our existence. If they were even slightly different, life would be impossible. Within the framework of the multiverse, this isn't a miracle, but simply the result of selection. We observe ourselves existing only in a universe where the conditions allow for our existence. This is known as the anthropic principle. Of course, the theory of eternal inflation remains, for now, a mathematical hypothesis that is impossible to test directly. We will likely never be able to peer into another bubble. Nevertheless, it elegantly follows from our best theories about the early universe and offers potential answers to many profound cosmological questions. Beyond the concept of eternal inflation, several other equally compelling hypotheses attempt to explain what might lie beyond the boundaries of our known universe. Many of these theories emerge from the intersection of cosmology and string theory, a leading candidate for the ultimate theory of everything, designed to unify general relativity and quantum mechanics. String theory posits that the universe's fundamental building blocks are not point-like particles, but rather tiny, one-dimensional vibrating strings. We perceive the various modes of vibration of these strings as different particles: the electron, the photon, the quark, and so on. One of the key requirements of string theory is that for it to be mathematically sound, it demands the existence of extra spatial dimensions beyond the three we are familiar with. This typically means 10 or 11 dimensions in total. This raises the obvious question: where are these extra dimensions? One traditional hypothesis suggests they are curled up or compactified down to microscopic sizes, making them virtually undetectable. But there is a second, more radical idea: the brane model derived from the word membrane. In this scenario, our familiar three-dimensional universe is just one of many branes floating within a higher dimensional space called the bulk. We and all the matter we observe, except for gravity, are permanently confined or stuck to this brane. It's like water droplets gliding across a pane of glass. They can only move in 2 dimensions across the surface, oblivious to the existence of the third. Gravity, however, according to string theory, is unique. It can penetrate this multi-dimensional bulk and spread out between the branes. This idea opens up startling possibilities. For instance, it offers a novel explanation for why gravity appears so weak compared to the other fundamental forces, electromagnetism, the strong and the weak nuclear forces. Perhaps gravity only seems weak because its true strength is diluted as it leaks into all the extra dimensions, while the other forces remain confined to our specific brane. Furthermore, the brane model allows for the existence of parallel universes that could literally be a millimeter away from us, yet remain completely inaccessible because they exist on a different dimension. Perhaps even dark matter, which we cannot see but feel only through its gravitational pull, is simply ordinary matter residing on a neighboring brane, interacting with us only via the leakage of gravity. The Big Bang itself might even be the result of a collision between two such brane universes. This is the so-called ekpyrotic model, which serves as a powerful alternative to the standard inflation theory. It proposes that the universe is cyclical, branes collide, triggering a hot, dense phase, which then expands and cools before eventually drawing back together for the next collision. While all these concepts remain on the cutting edge of theoretical physics and currently lack direct experimental confirmation, they demonstrate the immense scope for speculation when we attempt to look beyond the boundaries of our known world. This entire discussion about the edge of the universe, dark energy and multiverses inevitably pushes us beyond the realm of pure physics and into the sphere of philosophy. Understanding our place in this grand cosmic tapestry forces us to ask fundamental questions about meaning, purpose, and the uniqueness of our existence. Take, for example, the Copernican revolution. Nicholas Copernicus moved Earth from the center of creation, making it just one of several planets orbiting the Sun. Since then, every new astronomical discovery has only reinforced this principle of mediocrity. Our Sun turned out to be an ordinary star on the outskirts of a common spiral galaxy, the Milky Way. Our galaxy is just one of hundreds of billions in the observable universe. And now the multiverse theory suggests that our entire universe is merely a grain of sand on an infinite cosmic beach. This view can certainly seem disheartening. It strips us of any sense of exclusivity or centrality in the cosmos. Our existence appears to be the accidental result of nature's blind laws operating in just one of countless worlds. But on the other hand, there is a profound sense of grandeur in this realization. We are part of something unimaginably vast and intricate, and the mere fact that we, beings who arose on a tiny planet orbiting an unremarkable star, are capable of comprehending the laws of the cosmos, measuring the distance to the edge of the universe and contemplating parallel worlds. Isn't that miraculous? It speaks to the incredible power of the human mind. Furthermore, the concept of the multiverse and the anthropic principle force us to re-examine the question of why. Why are the laws of physics precisely the way they are? Traditionally, this question was answered either by religion, it is the divine design, or by science, which simply stated that they were givens, the initial conditions. The multiverse proposes a third path. The laws of physics in our universe are what they are, because if they were different, we wouldn't exist to ask the question in the first place. There are countless universes with different physical laws, but they remain barren and lifeless. Our existence is the result of a kind of cosmological natural selection. We live in a lucky universe. This perspective, while currently unprovable, is a powerful intellectual tool. It allows scientists to advance their understanding of the deepest mysteries of existence without resorting to supernatural explanations. The ever-moving edge of our universe is not just a physical phenomenon, it is the frontier of our knowledge. And as that frontier expands, so too do the boundaries of our worldview. Let's take a slight detour from the big global concepts and return to observational astronomy. How exactly are scientists today studying this expanding frontier and everything associated with it? We've already discussed satellites studying the cosmic microwave background, such as Planck, but that's only one tool. Another extremely powerful method involves studying the large-scale structure of the universe, specifically how galaxies and clusters of galaxies are distributed in space. This structure is not random. It resembles a gigantic cosmic web composed of dense threads known as filaments and nodes, which are the galaxy clusters crossing at points of high density. In between these are vast, almost entirely empty regions called voids. This structure is a direct legacy of those tiny density fluctuations we observe in the cosmic microwave background. Over billions of years, the regions where the density was slightly higher drew in more matter, eventually forming galaxies and clusters. Conversely, the less dense regions evolved into voids. By mapping and studying this web, astronomers can learn a great deal about the universe's fundamental parameters. For instance, this structure contains specific features called baryon acoustic oscillations, or BEOs. These are essentially frozen ripples in a pond, the imprint of sound waves that propagated through the primordial plasma before the moment of recombination. Today, the measured size of these ripples acts as a kind of cosmic standard ruler, allowing us to measure distances across the universe and thereby study the history of its expansion. To chart this structure, massive sky surveys are conducted, such as the Sloan Digital Sky Survey, or SDSS. In these projects, telescopes methodically image enormous swathes of the sky and measure the redshift for millions of galaxies, ultimately creating three-dimensional maps of the cosmos. These maps allow us not only to study dark energy but also to test general relativity on cosmological scales, measure the mass of neutrinos, and much more. Even more ambitious projects await us in the near future. For example, the Euclid Space Telescope, launched in 2023, or the Vera C. Rubin Observatory, currently under construction in Chile. These instruments will map billions of galaxies, looking further back in time and examining the epoch when dark energy first began to dominate gravity. They will provide us with unprecedented precision, which may finally help us unlock the nature of dark energy and understand why the boundary of our universe isn't just moving, but actively accelerating. One of the most intriguing and frankly disturbing puzzles in modern cosmology is what we call the Hubble tension. This refers to a significant discrepancy in the measured values of the Hubble constant, which is the key coefficient describing the current rate of the universe's expansion. This discrepancy arises because two different independent methods yield two different results. The first method is based on studying the local, or nearby universe. Astronomers measure distances to neighboring galaxies using standard candles, such as Cepheid variable stars and the type Ia supernovae we've discussed before. They then measure how quickly these galaxies are receding based on their redshift. By correlating this data, they get a direct measurement of the current expansion rate. The most accurate measurements obtained this way, largely thanks to the Hubble Space Telescope, yield a value of about 73 kilometers per second per megaparsec. To put that in context, it means a galaxy located 1 megaparsec away, that's roughly 3.26 million light-years, is flying away from us at 73 kilometers per second. The second method relies on studying the distant, or early, universe. Scientists use data on the cosmic microwave background radiation, or the CMB, gathered by the Planck satellite. As we know, the map of the CMB fluctuations holds complete information about the universe's parameters when it was just an infant. Using the standard cosmological model, which incorporates dark energy and dark matter, we can calculate how the universe must have evolved since then and predict what the Hubble constant should be today. And here is where the problem lies. The value predicted based on Planck data comes out to be around 67 kilometers per second per megaparsec. The gap between 73 and 67 might seem small, but the error bars on both measurements are tiny. This makes the disagreement statistically highly significant. The probability that this discrepancy is random is extremely low. This means something is fundamentally wrong. Either there is some hidden systematic error in one of the measurement methods that scientists haven't found yet, or, and this is far more interesting, our standard cosmological model is incomplete. Perhaps some additional physics was at play in the early universe that we are failing to account for. For example, maybe there were extra relativistic particles, often called dark radiation, or perhaps dark energy behaved differently in the past than we currently model. Resolving this Hubble tension is one of the primary goals of modern cosmology. It could well be the key that unlocks new physics beyond the standard model. Let's circle back to the geometry of the universe. We previously noted that observational data, specifically the analysis of fluctuations in the cosmic microwave background, CMB, strongly suggests that our universe is spatially flat. What does flat mean in practical terms? In a flat, or Euclidean space, our familiar laws of geometry hold true. The sum of the angles in any triangle is exactly 180 degrees, and parallel lines will never, ever intersect. If the universe had positive curvature, meaning it was closed, its geometry would be spherical, much like the surface of the Earth. In this scenario, the angles of a triangle would always sum up to more than 180 degrees, and parallel lines would eventually converge. This type of universe would be spatially finite but unbounded, similar to how the surface of a sphere works. Conversely, if the curvature were negative or open, the geometry would be hyperbolic, often visualized like the surface of a saddle. Here, the angles of a triangle would sum to less than 180 degrees, and parallel lines would diverge away from each other. This model implies an infinite universe. Now, the critical point is that observations confirm our universe is flat with extremely high precision. This precision is itself a cosmic puzzle, known as the flatness problem, which is precisely what the theory of cosmic inflation attempts to solve. Inflation proposes that while the universe, at its birth, could have possessed any curvature, the subsequent period of rapid exponential expansion effectively stretched space to such immense dimensions that, from our perspective inside it, it appears perfectly flat. Think of it like an ant crawling across a massive inflated balloon. The ant only perceives a tiny patch of surface, making the sphere appear flat to it. This suggests that our observable universe is only a negligibly small fraction of the entire true universe. The true global shape of the entire universe could still be spherical or hyperbolic, but its radius of curvature would be so gigantic that we simply cannot detect that warping within the limits of our current cosmic horizon. However, it's crucial to remember that while the universe's three-dimensional spatial geometry is flat, its four-dimensional space-time geometry is indeed curved. According to general relativity, this specific warping is precisely what we perceive as gravity. Massive objects, such as stars and galaxies, effectively dent the fabric of space-time, causing other objects to follow curved paths through this distorted region. Therefore, when we speak of a flat universe, it is vital to remember that we are referring to its large-scale geometry, independent of localized gravitational fields. We've spent a lot of time discussing dark energy, but we can't forget the second great cosmic enigma, dark matter. While it doesn't directly influence the accelerating expansion of space, its role in forming the structure of the universe, and thus shaping the world we see today, is absolutely fundamental. The first hints that this invisible substance existed emerged back in the 1930s. The Swiss astronomer Fritz Zwicky, while studying the Coma cluster of galaxies, noticed that those on the cluster's outskirts were moving incredibly fast. Their velocities were so high that the visible mass of the entire cluster, the stars, gas, and dust, was nowhere near enough to hold them together gravitationally. The cluster should have simply flown apart. To explain this stability, Zwicky hypothesized that the cluster contained a massive amount of some hidden dark matter, creating additional gravitational pull. His ideas weren't widely accepted at the time. But in the 1970s, astronomer Vera Rubin, while studying the rotation speeds of spiral galaxies, arrived at a similar conclusion. According to the laws of celestial mechanics, the orbital speed of stars should drop off the further they are from the galactic center, where the majority of the visible mass is located. However, Rubin's observations showed that the velocities of stars, even on the outer edges of galaxies, remained nearly constant. This could only be explained in one way, that galaxies are embedded in massive spherical halos of invisible matter that stretch far beyond the visible disk. Today, the evidence for dark matter is overwhelming. This includes gravitational lensing, the bending of light from distant objects by massive clusters, which reveals that their total mass is far greater than the visible matter alone. We also have data from the cosmic microwave background, CMB, whose analysis allows us to precisely calculate dark matter's contribution to the universe, around 27%. But what is this dark matter composed of? We know for certain what it is not. It is not ordinary matter, baryons, that simply fails to glow. It's not planets, cold stars, or black holes. If it were, there simply wouldn't be enough of it to account for the observations. Most scientists believe that dark matter consists of some type of exotic elementary particle that does not interact with electromagnetic radiation, which is why they are invisible, and interacts only very weakly with normal matter. These hypothetical particles are often called WIMPs, weakly interacting massive particles. Experiments worldwide are actively searching for them. Detectors buried deep underground to shield against cosmic rays are attempting to record the incredibly rare instances of a WIMP colliding with the nucleus of an atom of ordinary matter. So far, these dedicated searches have been unsuccessful, and the true nature of dark matter remains a mystery. But without it, our current understanding of the cosmos, including the dynamics of the expanding universe, would be fundamentally incomplete. Let's indulge in a little thought experiment and imagine a hypothetical traveler capable of moving at any speed, trying to reach the very edge of our observable universe. What would they actually witness upon arrival? First, it's crucial to realize that as they drew closer to this boundary, the boundary itself would perpetually recede. This is because their own observable universe would always be centered entirely on them. They could never catch up to the surface of last scattering that we see from Earth, because it isn't an object located in space. Rather, it is an event that occurred in the past. However, they could, theoretically, reach the physical location in space where, 13.8 billion years ago, the matter that emitted the cosmic background light we detect was situated. That spot is now calculated to be 46.5 billion light-years away from us. What would our traveler witness upon reaching this distant location? They would simply see a perfectly ordinary section of the universe, complete with galaxies, stars, and planets. For them, that location would certainly not be the edge. Their personal boundary would be 46.5 billion light-years further out in the direction they had just traveled. And if they looked back toward our position, they would see our home, the Milky Way, as it was 13.8 billion years ago, just a tiny embryonic structure within the background radiation field. This thought experiment underscores a key concept. The boundary of the observable universe is not a physical barrier, but a horizon that is relative to the position of every single observer. Every one of us, every galaxy, has its own unique observable cosmic sphere, and these spheres only partially overlap. This naturally leads to an intriguing question regarding the overall size of the universe. If we perceive the edge at 46.5 billion light-years, and an observer at that distant point sees their edge another 46.5 billion light-years further out, then the minimum size of the entire cosmos must be at least twice that distance. This straightforward logic proves that the universe as a whole must be vastly larger than the mere portion accessible to our vision. Estimates based on the observed flatness of spacetime suggest that the total universe, even if it is finite, must be at least several hundred times larger than our observable patch, and perhaps it is infinite. Ultimately, the journey toward the edge is a pursuit of a perpetually receding horizon, a quest that only serves to underscore the true, terrifying immensity of the cosmos. There is another paradox concerning the idea of an infinite and eternal universe, one that historically held great importance in cosmology, the photometric paradox, better known as Olbers' paradox. Its formulation is deceptively simple. Why is the night sky dark? At first, the question might sound naive, but if we assume the universe is infinite, uniformly filled with stars, and has existed eternally, then no matter where we look, our line of sight must eventually land on the surface of a star. This implies the entire sky should blaze with the same brightness as the surface of the sun. Night, as we know it, simply wouldn't exist. The paradox was formalized by the German astronomer Heinrich Olbers in the 19th century, though similar concepts had been discussed earlier. For centuries, it remained a profound cosmological puzzle. Today, thanks to modern cosmology, we understand the solution to this paradox, and it ties directly into the subject we are discussing. Olbers's paradox is resolved by two primary factors, both stemming from the fact that the universe is neither eternal nor static. The first and most critical solution is the finite age of the universe. Since the Big Bang occurred approximately 13.8 billion years ago, we can only observe light emitted by stars that lie within our cosmic horizon. Light from stars beyond that boundary, even if the stars themselves are infinite in number, simply hasn't had enough time to travel across the vast distance to reach us. Our observable universe contains a finite population of stars, and their combined light is insufficient to illuminate the entire background sky. The second solution involves the expansion of the universe. Light originating from distant galaxies that are rapidly moving away from us undergoes a phenomenon known as cosmological redshift. This expansion stretches the light's wavelength, causing its energy to decrease. For objects at extreme distances, this redshift is so pronounced that their visible light is stretched into the infrared and eventually into the microwave spectrum, rendering it invisible to the naked eye. This effect further reduces the overall luminosity of the night sky. Ultimately, the dark night sky we take for granted is, in itself, powerful observational evidence that we inhabit a dynamic universe with a clear beginning. The edge of the observable universe, its moving boundary, is precisely what allows us to perceive the darkness between the stars. Building on what we've discussed, it's worth taking a moment to address the so-called anomalies found within the cosmic microwave background, or CMB. While the standard cosmological model, LCDM, where lambda represents dark energy and CDM stands for cold dark matter, brilliantly explains the vast majority of our cosmic observations, the most detailed maps produced by the Planck satellite show certain peculiarities that don't quite fit the framework. These features aren't a definitive refutation of the theory, but they suggest either the possibility of new physics yet to be discovered, or perhaps they are simply statistical quirks. One of the most famous of these anomalies is the cold spot. This is an unusually large and extremely cold region in the CMB map. The probability that such a structure would arise purely by chance under the standard model is remarkably low. Various hypotheses have been proposed to explain it. Indeed, one of the most exotic suggests that the cold spot could be the remnant signature of a long-ago collision between our own universe and another bubble universe. A more prosaic explanation links the cold spot to a giant supervoid, an immense region of space relatively empty of galaxies located between us and the surface of last scattering in that direction. As light passes through such a void, it loses a small amount of energy, making that region appear colder to us. Another notable anomaly concerns the asymmetry of temperature fluctuations across the celestial sphere. One hemisphere appears, on average, slightly hotter than the other, a clear contradiction of the expected principle of cosmic isotropy. There is also the issue of the so-called alignment of the multipoles. Several of the largest scale features on the CMB map appear to be aligned along a single axis, sometimes dramatically referred to as the axis of evil. Statistically speaking, this alignment is highly improbable. For now, the scientific consensus leans toward treating these phenomena primarily as statistical fluctuations. They look unusual, yes, but they still fall within the bounds of what is statistically possible. After all, in any enormous data set, you are bound to find some strange patterns. Nevertheless, scientists continue to study these anomalies rigorously, as they might be the first subtle hints of physics beyond our current understanding, perhaps pointing toward a complex topology of the universe, or even to events that predated the Big Bang itself. The edge of the universe still holds its secrets close. Let's discuss the future of exploring the far reaches of the cosmos. What instruments and techniques will allow us to peer even deeper into the universe's secrets over the next few decades? One of the most promising avenues is gravitational wave astronomy. In 2015, the LIGO and Virgo observatories made history by directly detecting gravitational waves for the very first time, the ripples in space-time predicted by Einstein, resulting from the merger of two black holes. This discovery opened a completely new window onto the universe. Electromagnetic waves, like light and radio waves, can be absorbed or scattered by dust and gas, meaning they cannot bring us information about the very earliest moments of the universe prior to the epoch of recombination. Gravitational waves, however, barely interact with matter at all. They can travel straight through the universe without distortion. This means that in the future, using much more sensitive detectors like the planned space-based interferometer LISA, we might be able to detect gravitational waves born in the very first moments after the Big Bang, during the inflationary epoch. This would provide direct evidence of that era, allowing us to study physics at energies unimaginable and unattainable in any terrestrial accelerator. We wouldn't just be peering at the edge of the visible universe. We would be looking beyond it, right back to the beginning of time itself. Another crucial area is the study of neutrinos. Neutrinos are elementary particles that also interact very weakly with matter. There is a hypothesis concerning the existence of a cosmic neutrino background, analogous to the cosmic microwave background. These neutrinos decoupled from the rest of the matter just 1 second after the Big Bang, much earlier than photons. Detecting them is extremely difficult because their energy is so low, but if successful, we would obtain a snapshot of the universe at the age of 1 single second. Of course, classical astronomical observations will continue as well. New generations of giant ground-based telescopes, such as the Extremely Large Telescope, ELT, in Chile, and space observatories, the successors to the James Webb Space Telescope, will allow us to see the very first galaxies and stars forming in the universe, providing detailed insight into the epoch of cosmic dawn. These future discoveries will undoubtedly provide new answers, and perhaps more importantly, they will raise new and even deeper questions about the nature of our world and its ever-expanding frontier. A fundamental consideration when contemplating the boundaries of the universe is the nature of time itself. In our daily lives, we treat time as an absolute constant, flowing uniformly from the past to the future. However, Einstein's general theory of relativity demonstrated that time is profoundly relative. Its pace depends entirely on the speed of motion and the strength of the gravitational field. Time slows down dramatically near massive objects like black holes. Furthermore, for an object moving at a speed approaching the speed of light, time also passes more slowly when compared to a stationary observer. On a cosmological scale, time is still not an absolute constant. The expansion of the universe gives rise to a phenomenon known as cosmological time dilation. When observing distant objects, we don't just see their light redshifted, we also see that, relative to us, all processes occurring within them appear to be moving more slowly. For example, if we monitor a supernova explosion in a faraway galaxy, its light curve, the way its brightness changes over time, will be stretched out and lengthened when compared to an identical supernova closer to our own galaxy. This effect was predicted theoretically, confirmed by observations, and serves as further proof of the expansion of spacetime. This also implies that when we look toward the edge of the observable universe, specifically at the cosmic microwave background radiation, we are looking back at an epoch where time, from our perspective, was flowing millions of times faster. All processes in that young, hot, and dense early universe unfolded at an incredible, almost frenetic pace. Conversely, for a hypothetical observer in the extremely distant future, viewing our galaxy as it accelerates away from them, our time would appear almost completely frozen. The universe, therefore, represents a complex four-dimensional structure where space and time are dynamically linked and constantly changing. Understanding the true nature of time, what it is, whether it had a beginning, and if it exists in discrete quanta, remains one of the greatest unsolved problems in physics. The answer to this mystery is likely deeply interconnected with understanding exactly what transpired in the very first moment of the Big Bang, right at the edge of time itself. Up until now, our entire discussion has been based on the standard cosmological model, which posits that the universe originated from a hot and dense state following the Big Bang. But are there alternative theories? Yes, even though they are not mainstream, such models are actively being developed. One of these is the cyclic model we've previously mentioned, which is rooted in string theory and the collision of branes. In this framework, the Big Bang isn't the beginning of time. It's merely one stage in an infinite sequence of expansion and contraction cycles. This elegantly bypasses the problem of the initial singularity, a major mathematical hurdle in the Standard Model, where the laws of physics break down entirely. Another intriguing idea is the bouncing universe model. According to this theory, our universe wasn't born from a singularity, but emerged from the collapse of a previous iteration of the cosmos. When the collapsing universe reached a certain minimal but non-zero density, quantum gravitational effects caused it to bounce back and begin expanding. In this specific cosmological picture, time also had no true beginning. We also have more radical hypotheses. For instance, the steady-state universe model was popular throughout the mid-20th century, but was largely discredited by the discovery of the cosmic microwave background, or CMB. Modern variations of this concept try to explain observational data without resorting to the Big Bang, suggesting, for example, that the redshift of galaxies isn't due to expansion, but rather to tired light, the idea that light loses energy as it travels across vast cosmic distances. However, such alternative models face immense difficulty explaining the totality of observational evidence, particularly the high degree of uniformity found in the CMB. To this day, the hot Big Bang model, followed by inflation and accelerated expansion, remains the best description of the universe we have. It is supported by a massive body of independent observations. But science never rests. It is possible that future data will emerge, forcing us to re-evaluate our most fundamental understanding of the cosmos' origin and evolution. The edge of the universe that we currently study may turn out to be just one of many horizons in a far more complex and astounding reality. Let's pivot now to one of the most profound and unsettling concepts in our cosmic journey, the idea of the heat death of the universe. While this scenario is set in the unimaginably distant future, it forces us to contemplate the ultimate meaning and legacy of everything that has ever existed. If the universe ultimately degrades into a cold, dark, dead soup of elementary particles, does that mean all the achievements of civilization, all works of art, all accumulated information and knowledge are doomed to vanish completely without a trace? From a physics perspective, the answer is most likely yes. The second law of thermodynamics, which dictates that entropy, the measure of disorder, in a closed system can only increase, leads relentlessly toward a state of maximum entropy or thermal equilibrium. This is the heat death. All useful energy will be exhausted and all structures dissolved. However, even within this bleak picture, some physicists and futurologists attempt to find potential loopholes. For instance, there is a hypothesis that super-advanced civilizations in the distant future could learn to manipulate space-time, perhaps creating daughter universes in a laboratory and transmitting their essential information into them, thereby escaping the heat death of their parent cosmos. This is admittedly pure speculation, but it touches upon certain ideas within inflationary theory. A different, more philosophical perspective suggests that meaning lies not in eternal preservation, but in the sheer fact of existence itself. Even if humanity and all its creations vanish, the mere fact that matter arose in the universe capable of contemplating itself and the surrounding cosmos is an event of staggering significance. We are the universe's way of knowing itself. And even if this knowledge is fleeting, it is no less valuable because of its temporary nature. Moreover, the timescales we are discussing are so immense that they defy human comprehension. Trillions of years will pass before the last stars burn out. Before the final black holes evaporate, a googol 10 to the power of 100 years will elapse. Anything could happen in that time. Perhaps our current understanding of the laws of physics will change radically, revealing new, unimaginable possibilities. Therefore, as we ponder the moving boundary of the universe and its ultimate fate, it is crucial to remember that we are only at the very beginning of the journey of discovery. Our horizon of knowledge expands right alongside the cosmological horizon. In our lecture, we often use the analogy of the terrestrial horizon to explain the nature of the cosmological horizon. Let's delve deeper into this concept. When ancient mariners set sail on long voyages, they had no idea what lay beyond the horizon. To them, it was the edge of the world, a place where monsters might lurk or where the ocean simply dropped off into nothingness. But with every new journey, that horizon receded, and the world map grew increasingly complete. Eventually, through circumnavigation, humanity realized that the Earth had no edge. Its surface was finite, yet boundless. Something similar is happening with our exploration of the universe. Our cosmological horizon is our modern-day edge of the world. We cannot peer directly beyond it. But by studying what lies within this horizon, the cosmic microwave background, the distribution of galaxies, the laws of physics, we, like those ancient sailors, can formulate theories about what exists outside its bounds. Inflationary theory and the idea of a flat, immense universe are our equivalent of understanding the Earth's spherical nature. We extrapolate our current knowledge and assume that the world beyond the horizon operates under the same conditions as ours. However, unlike the Earth, we can never complete a cosmic circumnavigation to verify this. Accelerated expansion permanently prevents us from ever reaching those distant frontiers. We are confined within our observable bubble. This is the fundamental difference between modern cosmology and the geographical discoveries of the past. We have reached a limit that appears to be determined by the very laws of nature. This does not signal the end of discovery, however. It simply means we must develop more sophisticated methods to indirectly judge what lies beyond our visibility. The study of gravitational waves, neutrinos, and the search for traces of interaction with other universes in the cosmic microwave background, these are our new tools for mapping this terra incognita. The boundary of the universe is constantly moving, and alongside it, the boundary of our understanding shifts, perpetually challenging our intellect and imagination. Let's dive back into the numbers for a moment to fully grasp the sheer scale of the cosmos. The radius of the observable universe is 46.5 billion light-years. Consequently, its diameter measures 93 billion light-years. A light-year is the distance light travels in 1 year. That's roughly 9.5 trillion kilometers. When you multiply these numbers together, the resulting distance is almost incomprehensible. So, how many galaxies are contained within this immense volume? Estimates based on the Hubble ultra-deep field images suggest that the observable universe contains roughly 2 trillion galaxies. Each of these galaxies, in turn, harbors anywhere from hundreds of millions to hundreds of billions of stars. If we take a conservative average of 100 billion stars per galaxy, the total number of stars in the observable universe comes out to 2 times 10 to the 23rd power, or 2 tau 23. That's a number greater than all the grains of sand on all the beaches of Earth combined. And remember, that's only the observable portion. If inflationary models are correct, the entire universe is, by the most conservative estimates, at least 100 trillion times larger in volume. And perhaps it might even be infinite. Now let's talk about motion. We've established that the universe is expanding. The Hubble constant, typically cited as 70 kilometers per second per megaparsec, means that for every additional 3.26 million light-years of space, 70 kilometers per second are added to the recession velocity. Galaxies located at the edge of our event horizon, about 16 billion light-years away, are receding from us at speeds greater than the speed of light. Those at the very edge of the observable universe are rushing away at approximately 3 times the speed of light. This doesn't contradict the theory of relativity because it isn't movement through space, it is the expansion of space itself. These figures truly defy comprehension and leave us speechless. They highlight how infinitesimally small and insignificant we are on the cosmic scale. Yet simultaneously, the fact that we can measure these magnitudes while sitting on our tiny planet is the greatest triumph of the human intellect. We have learned to read the universe's book, written in the language of light, and its moving boundary is the final, ultimate page we are currently trying to decipher. To wrap up our long journey, let's mentally retrace our steps. We began with a simple question: does the universe have an edge? The answer we found is both yes and no. Yes, the part of the universe we can observe does have an edge, the cosmological horizon. This is the boundary in space-time from which we receive the oldest light, the cosmic microwave background radiation. This light was originally emitted when the universe was only 380,000 years old. But no, this isn't a solid physical wall where space simply ends. Beyond this horizon, the universe most likely continues identical to our own, but the light from those regions simply hasn't had enough time to reach us. We then discovered that this boundary is far from static. It's actually receding from us, and it's doing so at an accelerating rate. The driving force behind this expansion is the mysterious dark energy, perhaps the greatest enigma in modern physics, which is causing the fabric of space to stretch faster and faster. This runaway acceleration predetermines the ultimate fate of our world, a slow, cold fading toward heat death in the unimaginably distant future. It is also actively creating a cosmic event horizon which will permanently sever our connection to the vast majority of the cosmos. Using theoretical physics, we then peered beyond that limit, discussing exciting, though highly speculative, ideas like the multiverse, eternal inflation, and parallel brane worlds. These theories attempt to answer profound questions. Is our universe truly the only one? And why are its fundamental laws so perfectly fine-tuned for the existence of life? We also saw how the detailed study of this cosmic edge, from the accidental discovery of that faint background noise to the high-precision maps produced by the Planck satellite, transformed cosmology into an exact science. This enabled us to accurately weigh the universe, calculate its precise age, and determine its full composition. Finally, we realized that this ever-receding boundary is more than just a physical phenomenon. It is a powerful philosophical symbol. It symbolizes the edge of human knowledge itself, an edge that is constantly expanding, revealing increasingly grand and astonishing prospects. It reminds us both of our profoundly humble place in the vast cosmos, and simultaneously of the limitless potential of the human mind. We have traveled an incredible distance, from the earliest concepts of cosmic expansion to the boldest theories of the multiverse. We watched as scientists like cosmic detectives painstakingly gathered the evidence, the red shift of distant galaxies, the echoes of the Big Bang, the faint flashes of far-off supernovas. And all these clues came together to form a single, astonishing picture. Our universe has an observable boundary, the very light from its infancy. And this boundary is rushing away from us, dragging along galaxies that we will never be able to see again. All of this is driven by an invisible, incomprehensible force, dark energy, the nature of which remains the great mystery of the 21st century. This realization is simultaneously terrifying and awe-inspiring. We live in an age of great discoveries, but perhaps also an age where we are beginning to grasp the very limits of our comprehension. Thank you for spending this time with me, traveling to the far reaches of space and time. I hope this lecture was not only informative, but also helped you relax and prepare for sleep. Be sure to subscribe to the channel so you don't miss future journeys into the world of science. Hit the like button if you enjoyed this topic. And as you drift off to sleep tonight, consider this. What do you truly believe lies beyond our observable universe? Is it an infinite repetition of our own world, universes governed by different laws of physics, or something we cannot even begin to imagine? Share your thoughts in the comments below. Good night.